Hey everyone, so today we're going to graph rational functions. I want to kind of set you guys up ahead for this video. So in my classes, we last chapter went over vertical asymptotes, how to find those, and holes. So I might go through that quickly. The other thing with this lesson, because I didn't want to take too much time on writing things down, is I kind of wrote things ahead of time. So if you know that you would like to put them in your notes, make sure you pause, give some time to write that down in your notes, okay? So today, again, we are graphing rational functions specifically without a calculator. And we know with graphing stuff in the past, there's certain parts of a graph that allow us to tell which way it's going to go. And we have to remember a rational function is two polynomials over each other, right? That dividing. So that's why we have a P over Q. I always like to think of it as a numerator over denominator, that denominator specifically being something other than one, right? And of course it can't be zero. So this is the parent function of a rational function. As you can see, we have 1 over x, okay? So this is the most broke down, okay? And as you can see, we look at certain parts to this graph and we see that vertical asymptote that we were talking about last chapter. But if you also realize there's something else that's somewhat the same, but in a different form, and if you look, it's an asymptote right here. So one of the new things that we're going to do with graphing rationals is we're going to talk about what's called a horizontal asymptote. Horizontal asymptote meaning end behavior. Okay. So again, if you look at the bottom of your notes, we talk about the different types of asymptotes, right? So we have a horizontal asymptote, and that deals with what's happening at the end. We have our vertical asymptote, which of course we cannot cross over. It goes to infinity or negative infinity. Sorry, guys, my nose is stuffed. And then there's what we call an oblique asymptote, okay? Also, other people call it a slanted asymptote, because as you can see, you have a slanted line. This year, what we're going to do is I'm going to show you how to identify whether our rational function has a horizontal or an oblique asymptote. But this year, we're not actually going to find the oblique asymptote, okay? That's something we're going to do next year. And for those of you who were wondering earlier this year, why do we learn long division of polynomials? Well, that's how we get our slanted asymptote, is we have to divide the two out, long division. Okay, so again, recognizing it, but not finding it at this moment. All right. So another thing we want to do with all of our graphing is we have to find all these parts that will help us graph, and then we're going to put it back together. So here's the thing. Students ask me this all the time. Is this a hard concept? Well, no, I wouldn't say it's a difficult concept. I think it's more of a lot of pieces put together. So yeah, it takes some time, and it depends, I guess, if you would say time is difficult, right? So, all right. So a couple of the pieces that we're going to put together when graphing is the first thing we're going to do is find domain. We've been doing this for quite a while. Remember, in a rational, the denominator is not allowed to be 0. So those would be the values that we would restrict the domain from, okay? Then we would want actually, I like going vertical asymptotes first, because once we have our function and we reduce it, then we can tell between vertical asymptotes and holes. Remember, holes are what we crossed out, and then vertical asymptotes are what's left in the denominator, okay? So we set our denominator equal to 0 and we solve. Now, one of the new things I'm going to point out to you this year, we're not going to do anything tricky, but I do want to point it out. A vertical asymptote actually can be an even or an odd, okay? And you can almost think of it like a function, because an odd function, right? An odd function, the end behavior goes in different directions. Well, an odd vertical asymptote means that either side of that vertical asymptote are going in different directions. And by the way, this can flip-flop, okay? Where an even vertical asymptote has it go in the same direction. And this will help us later with graphing, okay? So we want to identify our vertical asymptotes as even or odd. I'm not going to trick you on that stuff though. I want you to picture it. Then remember what we crossed out is our holes. Now a hole is a coordinate pair. It's an x comma y. Remember how to find that y value is to plug that x value into the simplified function, okay? Now, let me go back up here because then I like doing my x-intercepts. X-intercept is when y equals 0, right? So it's a coordinate pair that has a number, comma, 0. Okay. Now, in a rational, right, we have a numerator, a denominator, right? Well, I want you to picture it. 0 can actually be written in multiple ways. 0 over 5, 0 over -2, 0 over 5,280. Those are all zeros. What is consistent? That the numerator equals 0, right? Because 0 over any number, 0 over any number equals 0. So when we're finding the x-intercepts for a rational function, just set our numerator equal to 0 and solve. The other thing we have to keep in mind about x-intercepts, and we learn this with polynomials, is that an x-intercept can touch or cross. Even odd, touch and cross, they both all come from the exponent of what we're looking at, okay? So that will make more sense as we start doing examples, right? And then, of course, to find the y-intercept, well, that's when x equals 0. So all we're going to do is plug in 0 for x and solve, okay? Now down here, it says stuff about sine waves. I'm actually going to not do sine waves today. I love sine waves. Believe me, I love them. Very important. But I actually want us to graph and think logically how this is going to form, okay? Even some people have you plug in points to see where it's going to be. I think you are so smart that you'll be able to do this logically. And then we're going to sketch our graph, okay? So let's do an example now. I usually write down all of my things that I want to find first, and then I graph. So if you want to pause the video to write that down, go right ahead. I'm going to start right in to this example. So the first thing I need to do is factor to see if we can reduce it in any way. So this is x minus 1 all over x minus 3, x plus 2. And as I can see, there's x plus 2, yes. As I can see, there's nothing we can cross out. Well, if there's nothing we can cross out, that means there's no holes. Now let's go to our domain. Remember, our domain says that the denominator cannot be 0 in any case, right? So that means our domain is going from -infinity to -2, -2 to 3, and 3 to infinity. Again, because what can't be here? Well, it can't be 3 and it can't be -2. Okay. Vertical asymptotes. Vertical asymptotes come from what's in the denominator, what makes the denominator 0 of the simplified. And technically this is simplified, right? So we have a vertical asymptote at 3 and a vertical asymptote at -2. Now, as you can see in the vertical asymptotes here, the exponents for both of those are 1, right, to the first. 1 is an odd number, okay? So I know both of these vertical asymptotes are going to be odd. So whatever direction is one side, the other side's the other. They're opposite, right? Okay, x-intercept. X-intercept, remember, comes from the numerator. What makes the numerator 0? Well, in this case, it is 1. Now we got to talk about touch and cross, right? So x minus 1 is to the first. It's an odd number, and odd exponents do what? They cross. Y-intercept is plugging in 0 for x. I like doing a little trick by looking back at my standard where it's all multiplied out, and I just cover up the x's, right? Because they're zeros. And as you can see, when I plug in 0 into x, I get 1, 6. So I have an y-intercept at 0, 1, 6. All right, and the brand new thing, horizontal asymptotes. So one thing I did not go over yet is I did not go over the cases because there are cases. So flip your page back over. I'm going to give you a rundown, and then we're going to go back to our example. So they put it as a N and M, but I'm going to put it in this form. So to figure out horizontal asymptotes and oblique asymptotes, what you're doing is you're looking at your leading term in the numerator and denominator. Okay, so I put a to the ax to the b all over cx to the d. Okay, so in case 1, if your numerator is smaller than your denominator, numerator is smaller than the denominator, your horizontal asymptote is at 0. Okay. Case 2. Excuse me. If your numerator and denominator equal each other, then your horizontal asymptote is at the leading coefficient, the AC. And as you can see, we are comparing exponents. And then in case C, if our numerator is larger than our denominator, then we have our oblique, okay? So 3 cases, and refer back to this all the time. This is the brand new stuff, okay? All right, so if we go back to our example 1, and I compare our numerator's leading term is x to the first, all over our denominator's leading term, which is x squared. As you can see, our numerator exponent is 1, our denominator exponent is 2. The numerator is smaller than the denominator, so that means we have a horizontal asymptote at y equals 0. All right, so now we're going to graph. Let's graph all of the pieces that we have so far. We have a vertical asymptote at 3. We have a vertical asymptote at 2, negative 2, I should say. We have an x-intercept at 1 and a y-intercept at 1, 6. Now, of course, just estimate where that's going to go. And horizontal asymptotes. Now, by the way, let's have this discussion. Asymptotes, we think of, hey, we can't cross. But if you remember, excuse me, I said earlier in this lesson that horizontal asymptotes aren't a full-on asymptote. It's talking about end behavior, guys. So when I graph, I actually just put my dotted lines at the end, which makes sense because look, we have an x-intercept. So wait, how can we touch or cross when it's an asymptote? No, it's a horizontal asymptote, so it goes on at the end, okay? Okay, now I want you to logically think what's going on here, okay? What do you know has to happen? And most people pause and they're like, yeah, I can't see it. Well, think of this. We have 2 coordinates here, and nothing's in between them. So if we have 2 coordinates, this x and y intercept, I know that somehow they must connect. They have to connect somehow. Okay, now let's put some pieces together. Well, first of all, this x-intercept, we said it crosses, so I know it has to come down here somehow. And the question is, will it go back up or will it stay down? Well, here's the thing. If we go back up, what do you notice it does? It crosses the x-axis again. But wait a second, we only have 1, so we can't come up. So we have to go straight down. Okay, and we get really close to that vertical asymptote. On the other side, again, that y-intercept here, we could technically come down, maybe, or we could go up. Which one is it going to be and why? Well, here's the thing. We're going to have to go up for the same reason on the other side there. We can't come down because we don't have another x-intercept. Okay, so now we have the middle part of this graph. And this is where our vertical asymptotes being odd is going to be very helpful for us. Okay, because on this -2 vertical asymptote, what that's saying is if this side of it is going up, that means on the other side, since it's odd, it has to go in the opposite direction. So it has to go down. Okay, now, do we flatten out or do we cross? Wait, we can't cross. We have no x-intercept. So this is just going to flatten out and get very close to our horizontal asymptote. Same thing on the other side. If this is going down, that means on the other side of the vertical asymptote, since it's odd, it's going to go up. And then we're going to curve out considering we have no x-intercept. And you guys just graphed a rational function without a calculator. So proud. Okay, let's do some more practice. We've got a couple more to do. Of course, I set this up already, right? All right, so we're going to have to factor it and we're going to have to simplify, okay? I'm going to factor this quickly instead of in parts, where you should probably do it in parts. Because, of course, this numerator, we can factor out a 2, and then we have the difference of squares. So we end up with x plus 1 times x minus 1. And on the bottom, it's a difference of squares. So we have x plus 2, x minus 2. Very good. Okay, nothing to cross off, so we know we have no holes. In our denominator, it can't be 0, so that's 2 and -2. So let's do that for our domain. So -infinity to -2, -2 to 2, and 2 to infinity. Vertical asymptotes, of course, are what makes the denominator 0. So that's -2 and 2. They are both to the first exponent, right? So that makes it odd. Sorry, I'm going a little fast, guys. X-intercepts come from the numerator. What makes the numerator 0? So we actually have 2 this time. We have -1, 0, and 1, 0. Keep in mind that x-intercept, y-intercept, they're coordinate pairs. So we need to write them that way. Y-intercept. Y-intercept is when the x's are 0. So I go back up to this one and I cover up my x's. And what do you know? I get -2 over -4, which is a positive 1/2. Horizontal asymptotes. Remember, we're comparing our leading terms. So in our numerator, our leading term is 2x squared, ... Our denominator is x squared, ... Our exponents, if we were to compare them, you would say they are the same. So since they are the same, that means we have a horizontal asymptote at 2 over 1, right? The coefficients in front. All right, now let's write down all the information we have. We have a vertical asymptote at 2 and at -2. We have x-intercepts at -1 and 1. And we have a y-intercept at 1/2. We have an end behavior. I like to say end behavior, right? Horizontal asymptote, end behavior at 2. Remember, I'm just doing that at the end. Okay. Logically, let's think about this. What happens? Oh, I forgot one more thing. Those x-intercepts, do they touch or they cross? Well, the exponents for both of them are 1, which is odd, so they both cross. Okay. All right, so what do I know logically first what happens? Well, I know all 3 of these have to connect. I also know the x-intercepts are odd, so they have to cross. Now what happens there? Do they come back up or do they continue going down? If they went up, we would have to have more x-intercepts. So unfortunately, that means they go down. I then know that these vertical asymptotes are odd, so they have to go in the opposite direction. So that means they're both going to be going up. I also know we have no other x-intercepts, correct? So I know that this is going to flatten out. Yay! All right. Now, as you can see in example 3, I have nothing written down ahead of time. Why? Why is that? Well, if you notice, the only thing I want you to notice here, because it is something I want you to be able to identify, is the numerator leading term over the denominator leading term. The numerator exponent is bigger than the denominator exponent. So what does that mean? That means we had a slanted or oblique asymptote. And I told you as of right now, we're not going to worry about those. Okay, what that would mean, guys, is when you graphed it, no matter how it is, there's going to be some sort of slanted asymptote. Okay. We're going to practice more of this later. Let's do our final one. Okay. And then you guys can get to some practice. All right. So if you notice here, and I'll break this down, this is x minus 3 all over x minus 3, x plus 3, which means we can cross out. So our reduced function is 1 over x plus 3. Okay. So we have a whole. Okay, so let's just go in order this time, so that way we don't have to go back and forth. Domain, remember, it's when the whole denominator can't be 0, right? So that's at 3 and negative 3. So our domain is negative infinity to negative 3, negative 3 to 3, and 3 to infinity. Our vertical asymptotes are what's in our simplified denominator, right? So what makes this 0? Well, that's x equals negative 3. Our wholes are what we crossed out, right? We crossed out an x minus 3. What makes that 0? Well, and that makes it 0 at 3. Okay, remember this is the coordinate, so I need to plug back in. I have to plug back into the, simplified. Okay, so if I plug 3 in for x, I get 1 over 6. So if you have to make a note to yourself, remind yourselves that you're plugging that in. Okay. X-intercept is when the numerator equals 0. So let's look at the numerator. Can 1 ever be 0? Nope. 1 can never be 0, so we do not have an x-intercept. Okay. Y-intercept, we're going to plug in 0 for x. I'm going to go to my original because it's really easy to cover up those x's. I have negative 3 over negative 9, which is 1/3. Okay, my horizontal asymptote, I'm looking at x in the numerator and x squared in the denominator. Our numerator is smaller than the denominator, so that means we have a horizontal asymptote at 0. See, I want you to take each of these parts. Do you feel that you could figure out vertical asymptotes? Do you feel you could do x-intercepts? Now we're going to throw it all together. Okay. All right, let's write down what we have. So at negative 3, we have a vertical asymptote. We didn't conclude. Is that going to be even or odd? What is that exponent? It's 1. So it must be odd. Let's do that for x-intercept. Oh, wait, we have none. Okay. All right, we have a whole at 316. So 1, 2, 3, and just estimate where that hole is, okay? No big deal, we're sketching. Our y-intercept is 0, 1/3. Now keep in mind that 1/3 is greater than 1/6, so our y-intercept is above our hole, okay? And then we have our y equals 0 horizontal. Okay. Now, just because we have a hole there doesn't mean the rest of the graph does not exist. So when I want you to think of things logically of how they connect and all that stuff, keep in mind that these are 2 coordinates, and these 2 coordinates must connect. It's just we have a hole there, okay? All right, so let's talk about the left side here of this y-intercept. Will it go down to this vertical asymptote, or will it go up to that vertical asymptote? Well, it must go up, because if it goes down, we would have an x-intercept, right? What about the right side of this hole? Well, the right side of this hole, could we go down? No, we can't go down. We have no x-intercept. So the only thing that we could think of doing is to curve out to that horizontal asymptote, okay? And then on the other side here, well, remember this vertical asymptote here is odd, which means it goes in different directions. So if this is going up, this one must be going down, okay? And we know there's no x-intercept, so we're gonna go across. Okay, take your time, think about your steps. Every little piece adds something to it, okay? So try to practice now. Thank you.